The request was to describe how deep space navigation works. And I had a dry run at this about a year and a half ago at my nephew's geomatics class. Well, we shouldn't skip to the end. I'm a navigation engineer at the Jet Propulsion Laboratory here in Southern California. And this was not done at government expense. There's two references here. Navigation Between the Planets by William Melbourne, Navigation 101. It was in Scientific American in June of '76. It applies today as much as it did back then. I had a minor role in that article. I was a member of the Viking navigation team, the cruise navigation team. Viking had orbiters and landers, two of them. So we needed a navigation team for the orbiters during the cruise and the landers for that part. And in this article, the very first plot is a history of the uncertainties of the Viking spacecraft as they were flying to Mars. And I produced the material that from a database I had. So having no qualms about plagiarism, I've captured a few figures from this paper, and we're going to go through them today. Now, if you really want to dig down deep and you have a radial telescope in your backyard of maybe 34 meters or so, although some people do it with 60 centimeters, the second reference is by an engineer here at JPL, former engineer, devoted his entire career to describing the mathematical equations to process what it is tracking stations measure and we do navigation with. Now, this is sort of the contents or the agenda. We couldn't track spacecraft if we didn't have the NASA Deep Space Network, and I'm going to try to show some videos that will give you a quick introduction to that. I need to offend you by describing some celestial reference systems, some astronomical coordinates. I'm sure right ascension and declination come up in your alphabet soup every morning. Talk about planetary ephemeris a little bit, what the data tapes are to do navigation, how we determine the spacecraft position. Everything's moving. But this article by Bill Melbourne, he was the manager of the navigation section at the time he wrote that. And there's a parameterization called the Hamilton-Melbourne parameterization that we're going to discuss today that describes how we navigate a spacecraft, what some of the limitations are to that, and how we can work that process backwards to derive and reduce the uncertainty on where the tracking stations are on the Earth. So the Deep Space Network is a bunch of giant antennae around the world that are used for tracking anything beyond the moon. Basically, we have 70-meter antenna. Does my mouse actually show on the screen? Yeah. So 70-meter dishes, you can see they're almost the size of a football field. We have a lot of 34-meter antenna. And I will attempt, now there's a couple of videos in here that kind of are DSN 101. And it looks like if I click on this, maybe they will jump into action. So here we go.
How do scientists and engineers communicate with faraway robotic spacecraft in our solar system? When scientists and engineers want to send commands to a spacecraft, they turn to the Deep Space Network, NASA's international array of giant radio antennas used to communicate with spacecraft at the moon and beyond. Operators at the Deep Space Network take commands, break them into digital bits, precisely aim these big antennas at the spacecraft, and send those commands to the spacecraft using radio waves. But what are radio waves really? Well, to start with, you probably already know they're part of the electromagnetic spectrum, which includes other kinds of waves and light that you're familiar with. Electromagnetic energy is a type of energy that can travel through space as waves that have different properties, depending on the size and spacing of the waves. These waves span a broad spectrum, from very long radio waves to very short gamma rays. The human eye can detect only a small portion of this spectrum, which is why it's called visible light. Radio waves are the longest in the electromagnetic spectrum, and the wavelengths used by the Deep Space Network currently range from about the size of a dime to the size of a dollar bill. Radio waves are all around us. We use them when we listen to music over the radio, or send emails from computers using Wi-Fi, or when we talk on cell phones. Computers and cell phones are actually just high-tech radios. Radio waves also travel really, really fast, at the speed of light. That's 186,000 miles per second. But our solar system is also really, really big. It could take several minutes or even hours for the radio waves to reach a spacecraft. Once spacecraft receive the signal, they execute commands, collect scientific data and never-before-seen images, and send all of that data back to Earth as digital bits, which are gathered by the huge antennas of the Deep Space Network and distributed to scientists, allowing them to learn a little bit more about how our solar system works. Has dozens of robotic spacecraft exploring our solar system and beyond. So how exactly do we navigate spacecraft that are so far away?
Hey Neil, can you turn it up a little? It's quite quiet on our side.
Can use precise
There we
measurements
go, that's
to know
great.
where
Thanks.
faraway spacecraft are by using the Deep Space Network, NASA's international collection of giant radio antennas used to communicate with spacecraft at the moon and beyond. Before a mission, engineers and scientists carefully plot a spacecraft's journey. After launch, we know how far away a spacecraft is by using the Deep Space Network to send radio signals to the spacecraft and measuring the time it takes for those radio signals to be received by the spacecraft and transmitted back to Earth. We can learn how fast a spacecraft is moving by measuring the Doppler shift. As the distance between Earth and the spacecraft increases, radio waves from the spacecraft will appear at a lower frequency. If the distance between Earth and the spacecraft decreases, radio waves from the spacecraft will appear at a higher frequency. Doppler shifts happen around us all the time. It's the reason why a siren sounds higher in pitch when it approaches you and then lower in pitch as it goes away. Using the Deep Space Network antennas, mission controllers can determine the position and speed of a spacecraft with great precision. If the spacecraft needs to adjust its course, they can send commands to the spacecraft through radio waves to change its trajectory. Using these techniques, engineers and scientists on Earth can bring a spacecraft to a precise landing on Mars or into an orbit around another planet in our solar system after a journey of millions of miles. Without the many antennas of the Deep Space Network, NASA would not be able to navigate or talk to any of the faraway spacecraft exploring our solar system.
Yeah, as you saw in the video, we have complexes around the world, about every 120 degrees. The ones in Goldstone, California are outside Los Angeles near Barstow. And then we have some in Canberra, Australia, and also Madrid, Spain. And each station has a number. When there's a wiggly thing going up, that means we're transmitting to a spacecraft. If it's going up and down, we're transmitting and receiving. These are icons of the station. There's a 70-meter dish at each complex. These can detect the energy of a match at the distance of Mars. And at the top here is the name of the mission that's being tracked at the moment. So this one is OSIRIS-REx. We're transmitting to OSIRIS-REx, which brought samples back from asteroid Bennu. This is the James Webb Space Telescope. We're transmitting and receiving to that from this station in Madrid. These others happen to be idle at the moment. Here at Goldstone, we're transmitting, I believe this is the Korean Lunar Orbiter. We're transmitting and receiving. Down here at Canberra, we're transmitting to Solar Probe Plus. That's Parker Solar Probe, which is a Johns Hopkins mission. It's orbiting the sun. And at the website that was in my PowerPoint, you can pull this up anytime and see what's going on in the DSN. If you click on an antenna, then there's information over at the right here, such as this really was OSIRIS-REx. I got it right. And this one is James Webb Telescope. It tells you the azimuth and elevation of the station And if nothing else, that'll probably cure your insomnia. So DSN in action. Okay, now let's get on with things. I wanted to find the celestial reference frame, and here's a picture. I'll spend just a little bit of time on this. Obviously, here's the Earth in the middle. The celestial equator, of course, is just an extension of the Earth's equator. Longitude is measured from the Greenwich meridian. It can be measured east or west. We tend to measure it east here. Then the celestial sphere, here's the North Celestial Pole, and the vernal equinox is where the ecliptic, which we see here, intersects the celestial equator, which is the extension of that. And right ascension is measured eastward from the vernal equinox along the celestial equator. And of course, declination is north and south of the celestial equator. And of course, over on the other side is the autumnal equinox. Now,
So the vernal equinox is the 0, 0 point on the spherical graph.
yeah, that's where the sun is on the spring or first, March 20th. The sun is going from below the celestial equator. There's a plane crash as it goes through it and becomes above it. Now, this direction, this vernal equinox, this is a reference for lots of things, stars, planets, and the moon. Their right ascension and declination is all measured and determined with respect to that. You got to remember that. So you're all very familiar with this kind of stuff. Longitude, latitude, right ascension, and declination. I'm kind of preaching to the choir here. And of course, one thing perhaps I should emphasize is that the stations on the DSN, of course, are sitting here on the Earth. And so their coordinates are basically latitude and longitude and distance from the center of the Earth, you might say, in a body fixed frame. Longitude is measured from the Greenwich meridian, latitude north and south of the Earth's equator. So a major part of navigation is relating where the stations are, starting with where they are in the surface of the Earth to where are they in inertial space. So with that, I guess maybe one thing I might dwell on is the planetary ephemeris. This is a computer file of the time-varying positions and velocities of the Earth and the other planets. You might say it's a map of where everything is, where things are in the solar system, the center of the Earth, the center of the moon, or the barycenter about which they revolve. And the position and velocity of the planet at any time can be found from the planetary ephemeris. Now, developing the planetary ephemeris is much like navigating a spacecraft. We make measurements of where the planets and the moons are against the background stars, and Newton's laws of motion describe the motion of those bodies in the solar system. So we have those observations and we fit them to a mathematical model. And instead of deriving the trajectory of a spacecraft, we derived the trajectory of a planet. And these then form the basis of navigation. We have to know where we're going. And this is the source of that. Now, one of the things I indicated down here near the bottom in kind of the blue is that the accuracy in the 60s had huge errors in it because it was based solely on measurements from astronomers with Earth-based telescopes. And we discovered when the radio scientists started bouncing radar signals off Mars that there was a huge error in the astronomical unit, which is the yardstick by which the we scale the size of the solar system. The astronomical unit is the average distance the Earth is from the sun.
So it was the astronomical unit that was off by 66,000 kilometers?
Well, the position wasn't 66,000 kilometers. I don't know the exact error in the astronomical unit, but a tough decision had to be made. Do we go with the classical astronomers' value of the astronomical unit, or we do use from these new radar scientists? Well, they chose the scientists, and it's a good thing. Otherwise, we would have flown on the other side of the planet. So, what do we measure to do navigation with? As you saw in those videos, we're measuring the line of sight velocity and the time it takes a signal to go to the spacecraft and back from a station on the Earth. And in a two-way coherent mode, the tracking station is continually transmitting to the spacecraft, and it's multiplying the frequency up so it isn't confused with the downlink signal and sends it back. And that coherent data is the basic data by which we do navigation. Now, let's see what's coming here. Everything's moving. The spacecraft is moving in respect to the Earth, so it sees or receives a signal whose frequency differs from the one that's transmitted. And we talked about this Doppler effect, depending if the object is receding from the station or it's approaching it. And we can measure radio velocities down to 1/10 of a millimeter a second with this kind of stuff. Now, to understand this parameterization, which is a simplified way of understanding why navigation works, I wanted to make sure that I defined the coordinates we use for the stations for navigation. Now, instead of thinking of the Earth as a sphere, think of it as a cylinder, which I've indicated here with this black circle. And somewhere on the surface of the Earth is a tracking station whose distance r from the axis of rotation. This is the cylindrical radius or distance from the spin axis, and we work in the metric system with that. So this is in kilometers. Now the longitude, of course, is measured east from the Greenwich meridian. And to complete the distance, the distance from the equator plane, we call that the z height, completes the definition of the location. Now you can also, at this point, I want to indicate that the velocity of the station, just due to the rotation of the Earth, of course, is a function of the distance from the center and the rotational rate of the Earth, which, is 360 degrees every 24 hours. And then it's an easy extension from that at the equator, that velocity would be the maximum. And conversely, at either pole, it would be zero. And of course, our stations are at different cylindrical radii and different longitude and different heights from the equator. So we've replaced the geocentric radius with the cylindrical radius because we need to define the station velocity. And with that, let's kind of blow this wide open. And here is a spacecraft, and here is the Earth. Here's a station. The Earth is rotating, and the measurement from the spacecraft, rho dot, the range rate, is a function of the range rate of the spacecraft and the velocity of the station times the cosine of the declination of the spacecraft, and also where it is relative to the station longitude and right ascension. So if the declination were 90 degrees, the spacecraft was straight overhead, we wouldn't see anything in the line of sight here. It would just be the geocentric velocity. And maybe we'll come back to that, but here's kind of an overview of what's going on. And I want to emphasize, we think of the right ascension of the spacecraft against the celestial sphere but we're also going to have to define the right ascension of the station in inertial space. And that's going to involve mainly knowing what time it is on Earth so that we can rotate through that angle from the vernal equinox to where the station is at any particular time. Now, if we look at the signature in the tracking of a spacecraft as shown in this curve, let's assume that the spacecraft is not moving relative to the center of the Earth. So this line along here is the geocentric velocity. This would be the velocity of the spacecraft relative to the center of the Earth. But here on the stations, when the spacecraft rises, the velocity is going to decrease. And just as the spacecraft goes over the station meridian, there will be zero velocity. And at that time, the right ascension of the spacecraft is equal to the right ascension of the station, which of course all gets tied back to where the vernal equinox is. And as the pass continues, of course, then the velocity is going to maximize up here until it sets. And then, of course, it's behind the Earth here, but this signature repeats every day. So for starters here, if at this point, when there is no measured radial velocity, we know that the right ascension of the spacecraft is the same as the right ascension of the station. And if we know where the right ascension of the station is, we're on our way to understanding how navigation works. Now, the amplitude of this curve is a function of how far the station is from the axis of rotation, this cylindrical radius, and the cosine of the latitude. And this amplitude is a function of the cylindrical different distance from the spin axis and the cosine of the declination of the spacecraft. So I've given the whole secret away.
So you're getting the illusion, if I understand this, that the spacecraft is based on Doppler shift is speeding up and slowing down, when in fact it's not. It's the spinning of the planet.
Yeah. Right. In this visualization, we've assumed that the spacecraft is not moving with respect to the center of the Earth. Let's zero out the geocentric velocity for the moment. But of course, in reality, it is moving. But it's this signature. If the Earth did not rotate, we would not be able to do deep space navigation. And you can see if we don't know the right ascension of the station, i.e. the station longitude when this velocity is zero here, we can't get the right ascension of the spacecraft. And conversely, if there's an error in our knowledge of how far the station is from the cylindrical axis of the Earth, its distance from the cylindrical axis, we don't know what the amplitude of this curve will be. Clear as mud, right?
Clear as mud.
I have a question. You might have to relay it in.
Yeah. Liam has a question.
Since we show here that we lose signal on the far side of the Earth, do we do signal handoff between the stations so we can maintain communication, or do we pause because each station is dedicated to?
All right. So Liam is asking about the handoff between, because the Earth is spinning. So you've also got a handoff between the three antennas?
Oh, yeah, for sure. And with those antennas spaced about every 120 degrees, we can track 24 hours a day.
So we never have signal degradation and loss then because we can maintain it as we rotate out.
We're sensing this signature, whatever station is tracking. So summarizing this, from the Doppler tracking, from its rising to its setting, it's possible to extract estimates of the right ascension and the declination. And as I said, and as we're showing again here in the lower right, when these two curves intersect, the spacecraft is crossing the station's meridian. And if we know the longitude of the station and can accurately compute its right ascension relative to the vernal equinox, then we're on our way to accurately determining the right ascension of the spacecraft. And the amplitude of this that we compute is going to be based upon our knowledge of the distance the station is from the rotation axis of the Earth by the cosine of the declination. And from that, we derive the spacecraft right ascension and declination from multiple passes from multiple stations over time. But this is the simple parameterization of where the information content comes from.
Question.
Yeah,
So how would this work if we were on the moon?
not very well, because the moon's rotation is very, very slow, is what you're getting to, isn't it?
Yes.
And I said, if the Earth did not rotate, we wouldn't be able to navigate. So it'd be a real challenge from the moon. Maybe is something you can visualize because it's very slow.
And you mean, because you put it on the moon's pole, it would get obscured by the Earth, so you'd have to lose it anyway. But if it's
27 days.
yeah, it wouldn't work. Yeah.
So summing this up, how does the station location error impact navigation? The accuracy for right ascension and declination highly dependent upon accurate knowledge of the tracking station longitude and distance from the Earth's axis of rotation. So an error in longitude introduces a corresponding error in right ascension, and an error in the value of the distance from the spin axis introduces a corresponding error in the value of the declination. That's bottom line. And when I started here, well, let's not start here yet. Here shows how a small error in longitude magnifies when you're computing a spacecraft right ascension. Here we are with a polar view of the Earth. We're looking at this cylinder again, and here's a station somewhere. And if we have a longitude error of 3 meters in where we think the station is in our computer program, by the time we get to Mars, that's equivalent to 90 kilometers. And 350 kilometers at Jupiter and 700 kilometers at Saturn. Now, so when I came here, the task was to improve the accuracy of deep space navigation by reducing the uncertainty in the tracking station locations. Because if you don't know where the stations are, you can't determine right ascension and declination. Now, of course, traditionally, the location of any particular spot on the Earth is determined by geodesists, and they introduced this concept of a datum, which is a mathematical model of an ellipsoid or something that we think best represents the surface, let's say, of North America. And these datum are all over the world. So we know where the Goldstone stations are on this North American datum. Down in Canberra, we know where the station is on some Australian datum, and likewise in Madrid. But we don't know where these datum are relative to the center of the Earth. And that's the limiting factor there. Where the spacecraft is responding to the velocity of the center of the gravity of the center of the Earth, and we need to know where we are relative to the center of the Earth. So now we're going to play the game backwards. We've got all this signature in the tracking data, and now if the right ascension and declination of the spacecraft, I use the term anchored here to a planet or the moon by passing close by or orbiting it. For example, there was 4 Ranger flights, 6, 7, 8, and 9, that impacted the moon. They were taking pictures for the Apollo program. So after the last mid-course trajectory correction maneuver to hit the moon, we can use the Doppler tracking from all the stations And since now the gravity of the moon is defining where that spacecraft is in the celestial reference frame, and we can use the amplitude of that topocentric Doppler in reverse to estimate the location of the tracking stations. And in Melbourne's article, it says this is good to about 1 meter. And it's relative to the center of the Earth. We've jumped off that datum to those are no longer an issue. Now we're determining the locations relative to the center of the Earth. And when I started here, those 4 Ranger missions had been used to do that. In the last few hours or maybe day of a mission, when there was just free flight ballistic trajectory to the moon, the same navigation software that estimates the spacecraft location can be also used to estimate the tracking station locations. So we had that for the 4 Ranger missions. And then we statistically combined that. We had 4 independent measurements. So when you combine them, we're reducing the uncertainty in the station location. So now for the next mission, we can tighten the navigation requirements that we can meet for the scientists and fly closer to a planet or maybe land in a better spot and do more science. So this kind of sums up what I just have been saying. What were the sources of location estimates in 1968 when I came here? So I've described how this Doppler signature is used in reverse. And I mentioned there were the 4 Ranger missions that had been combined with station locations, and that was our reference set. Well, then in the mid to late 60s, Mariner 4 flew by Mars. Mariner 5 had a Venus encounter, and we estimated the station locations from those planetary encounters because the planets defined the right ascension and declination of the spacecraft at that time. And based upon the signature in the tracking data from that, this reverse process gives us station locations. However, I remember in January of 1968, JPL gave me an electric typewriter, and I typed on the back of the wide computer paper, and I had the station location solutions from the Ranger missions and from Mariner 4 and Mariner 5. And I concluded that there was definitely a difference in the station longitudes between the locations derived from those 2 sets of missions. It was about 20 meters, 20 times 10 to the minus 5th degrees. And I say, ouch. So we need to resolve this lunar and planetary-based longitude difference. One of the engineers, scientists here who was responsible for developing the planetary ephemeris, forwarded this enigma to an astronomer at the U.S. Naval Observatory, Tom Van Flandern. And he understood how our lunar ephemeris and our planetary ephemeris were derived. And the root cause of this difference was that the origin of the right ascension, i.e. where the vernal equinox, was not the same in the lunar and the planetary ephemerides. And the difference? It explained the difference we saw in the longitude estimates when we got the missions that were flown to the moon or had been by the planets. Now, let's see here. I'm kind of trying to visualize that. We've got a tracking station here, and we have 2 kind of one-dimensional coordinate frames. Here's frame A, and its x-axis is along here, and here's an A prime, and its x-axis is along here. And what is the tracking station location? Well, in frame A, I claim it's 3, and in frame A prime, I claim it's 3.3. Well, why does it matter? We need to think about the size of the solar system a little bit. But let's say you want to tell somebody where to find the station. you need to define what coordinate frame they need to use to make that determination. So this is what Tim was pointing at, a real life story about these coordinate frame differences. In August of 68, well, prior to August of 68, but by not too much, NASA decided that the Apollo 8 mission was going to be a manned lunar orbiter, not an Earth flyby, or not an Earth orbiting mission as originally been planned. There was a lot of concern that the Russians were going to beat us to the moon. The lunar lander was not ready. And literally about 4 months before this mission launched, there was a major decision made that Apollo 8 was going to be a lunar orbiter with a crew of astronauts on board. Furthermore, it was going to use a Saturn V rocket, which had, I think, blown up on its previous launch. And Johnson contacted us, and they want us to kind of look over their navigation shoulder and see if we could maybe poke at anything that might limit their navigation. They had no deep space navigation experience. When you're orbiting the Earth, no matter what you do in 90 minutes, it'll be around again. But when you're flying into deep space, as I showed back here, if you have an error in your station locations, where you think the spacecraft is not where it actually is. Now, sure, when you finally get to the moon or the planet, the gravity of that planet will tell you where it is, but unfortunately, you don't have time to correct the error in that position because you don't feel these planets until you're very close to them. So you've got to have this right when you start. So we decided by simulating some data, we simulated the approach of Apollo 8 to the moon. And when we simulate the radiometric tracking data, of course, we make assumptions about the mass of the Earth and where the moon is and where the tracking stations are. And then we could reprocess that as if it were real tracking data by making various changes in our observational models. So one of the things we would change, of course, would be the station locations, and we would use the erroneous values for these to assess how much the trajectory was in error by the time we got to the moon. And when we got all done with this, we also realized that the Johnson Space Center, the Apollo program, was going to use the same lunar ephemeris that the Ranger missions had used to derive the station locations for the DSN. So the conclusion was we would take those station locations and we would make some corrections for the predicted polar motion and the difference between UT1 and UTC, and supplied the Manned Spacecraft Center with those station locations with those corrections. I have no idea what became of that. They used them in a back room somewhere for backup navigation. They had problems finding a computer where they could put the station locations in at the meter level. All I know is on all successive lunar missions, they would call me up and say, "Can you do the same thing again?" So maybe if we go back to this is basically why we had difference in those station locations. We had two different reference frames. And it's not that one is right and not that the other is wrong. It's just that they're inconsistent. They're biased relative to one another. And if you have a bias between things, you don't want to take the average value because that's not correct in either system. So we knew what coordinate frame that they knew where the moon was in. So they needed station locations that were consistent with that. And now you're probably all thoroughly confused and you would have been scared to death to be an Apollo 8.
The polar rotation pattern changed from the previous slide.
Oh, he's asking about something about the previous slide, Neil. Something about polar rotation.
Yeah, the polar motion.
Polar motion?
Yeah, predict the polar motion. What does he mean by that?
The instantaneous axis of rotation of the Earth wanders around an area about the size of a tennis court.
The wobble, okay.
This is not precession
Yeah,
or
yeah.
rotation. It's actually a motion due to maybe land masses, winds, ice, and it can be measured. It's very difficult to predict. So we made an estimate of where we thought it would be at the time of those missions. That's one of the things that changes. Now, UT1 minus UTC, UTC is basically Greenwich Mean Time, but UT1 gives you the true orientation of the Earth. You know, time is just an angle. And UTC runs at a more or less uniform rate, but UT1 reflects the true orientation of the Greenwich meridian, you might say, relative to the vernal equinox at any given time. Does that help?
Yeah, that explains it. Thank you.
Good question. I guess that's where I was. That's navigation. If I haven't put you all to sleep, my story a little bit, if I still have some time. I grew up southwest of Chicago. This was my dad planting corn in 1941, a 2-row horse-drawn corn planter. That's the farm we grew up on. He was born in the front room of that house. He later switched from farming the land and feeding cattle to chickens. He injured himself digging frozen cattle feed out of an outdoor silo one winter, and he lived on painkillers for half his life. But he had the 4,000 chickens, 2,000 eggs a day. And that's also my sister there. There was always something to do. We had 2,000 eggs a day to candle and pack, and those 4,000 chickens. Anytime you got livestock, you got a lot of concern. One of my favorite authors is James Herriot, the Yorkshire vet that wrote All Creatures Great and Small in that series. So my mother arranged for us to look through a homemade telescope just like this that was assembled by a neighboring farm lad. He ordered the mirror and the pieces from Edmund Scientific. I can still remember seeing craters on the moon looking through that telescope one night. I was a junior in high school, excuse me, and that got me interested in astronomy. Back in those days, you had to write a letter to get a catalog from anybody, so I wrote to Edmund Scientific and ordered a catalog, and they had a nice page in there that told you what pieces you need to make a telescope. So I ordered a 4¼ inch spherical mirror and a plastic eyepiece holder and just a plain flat mirror for a diagonal. And my dad wrote a check for $28.05.
Wow.
I went to a carpet store and got a cardboard tube, and these 2 straps are actually belts that I had from Civil Air Patrol uniforms when I was in high school. This, you can't quite see it here, but there's a piece of eaves trough is the semicircular support here for the telescope. This is plumber's pipe. These are clamps for my dad's cultivator. This coffee can was full of screws and things for a counterbalance. And Christmas present one year was this finder scope. Originally, I had to stare up the end of the tube, which I'm sure a lot of you have probably done too. My parents knew that there was no future on a 200-acre farm. And I can't remember when I wasn't going to go to school, and hopefully an education would be my ticket out of there. And this interest in astronomy set my course. I majored in it in school. I went to a junior college my first year, and then I transferred to the University of Illinois, Urbana. Majored as astronomy major, a math and physics minor. In order to graduate in 4 years, I took computer programming and zoology in summer school. And I nearly flunked computer programming and went on academic probation. That pretty well took care of graduate school. I applied to several. Of course, that academic probation stamp on my transcript didn't help any. But I interviewed about 4 aerospace companies. This was on the campus in Urbana, Illinois. JPL was one of them. I'm still waiting to hear from them. They said they'd keep my resume on file. Excuse me. One company, Northrop, offered me a job. I bought my parents' car. My dad and I drove to California in 1966. I ended up working for Northrop. We were building a catalog of Earth's islands and lakes that satisfied certain sizes and isolation criteria. I had access to all the maps that the Air Force pilots use. And I would find islands and lakes that satisfied these criterias, and I'd take a piece of tracing paper and outline it and write the location down and punch 3 holes in it and put it in a binder. They were going to put this catalog on a Earth orbiting satellite that could sense these features, and based upon the difference between the sensed position and the catalog position, update its orbit. And ships at sea would be able to interrogate this satellite. You know, if you stretch it about 5 orders of magnitude, it sounds like GPS. Excuse me. That job ended in about 6 months. And they said, well, we send our guys to JPL. Would you like to go? Wow. That was about a year after that ill-fated interview with a JPL recruiter. And I landed in the middle of that group that was trying to improve navigation accuracy by reducing the uncertainty in the station locations. And I've been involved in deep space navigation ever since. Looking backwards, the best thing that could have happened to me was not getting into graduate school at the time. I would have studied the wrong thing. I'm not an academic standout. In fact, I'm the only person that has a modern scripting language named for their GPA, and that's C++. However, after a couple of years at JPL, I discovered what I did need to major in, and I found a school that would cater towards that. JPL paid the tuition, of course, and I submitted a computer program I wrote here at work. Pardon me. So, life in the rearview mirror is very interesting. I wish I could look through the windshield with 10% of what I see in a rearview mirror, and I'm not shy about saying it has to be divine intervention. I look at the forks in the road, starting on that farm. And thanks to Ole Olson at Ash Manufacturing, he had very little work for me. But he would always mail me his copy of Sky and Telescope that he got for running an ad for Ash Dome in that magazine, and encouraged me in that. And when I switched from contractor to JPL, they handed me this pamphlet, and it said, "You've been hired for one of 3 reasons: outstanding academic performance." Oh yeah, right. I haven't told you about German. It took 3 years to get credit for 2 years and year-round tutors and dropping courses in the middle of the term, expecting failing grades on my transcript. So I don't think it was my academic standout. Or the second reason, because of your work experience. Tracing islands off maps is not going to get you a Nobel Peace Prize. And the third one must be your character. So it was the work ethic and the character. My mother was a school teacher, as I mentioned, and her expectations were, I know you're not Einstein's. I don't expect that. I just want you to try and do more than is asked. Now, with those 4,000 chickens, I'd better be on that school bus every night. They don't have time to drive to school and get me. They can't afford a car for me. I better be on that bus and get home. But if I needed to stay after school and talk to a teacher, and sometimes it only takes 5 minutes of repeating an explanation, you know, and the light bulb goes off, and they would come and get me. So I guess that's kind of my story in a nutshell. For some reason, I'll never know why, my high school science teacher taught his entire career in this little school. There were 71 in my graduating high school class. And in the 70s, when I had been working here for maybe 10 years or so, for some reason I wrote to Mr. Potts and said, I'd like to come and talk to your classes. And he arranged for me to talk to his classes, and one year his son was in that class, whom I did not know. The first time I met him, he was still in the oven.
Yeah.
And in 45 minutes, I set his career, and he went to the University of Illinois, majored in aerospace engineering. And unlike me, he got hired straight away here at JPL. We were in the same section for many, many years. And
Neil, Neil, I got a question. They just recently launched the space plane, and that has an experiment for quantum navigation. Are you familiar with that experiment that they're doing?
nope.
Good answer.
Yeah.
I do know one of the things, a spacecraft transmitter radio, if you turn it on, of course, it's going to transmit a signal. And we can receive that signal here. We call it one-way Doppler, you know, the spacecraft is transmitting. But those are not ultra-stable oscillators. And that signal is so noisy that tracking from a single station, you cannot do orbit determination with that. If you're tracking, let's say, from two different complexes, Goldstone and Canberra, and they're both receiving the one-way data, you can effectively difference that and extract information because the noise is common at both stations. It originated on the spacecraft. Now, there was an experiment here several years ago. I believe it's over, but they wanted to launch a deep spacecraft with an atomic clock.
That's what this experiment is. They're
And
proving it now, I guess. I guess they're supposedly taking it to almost absolute zero and then shining a laser at the atoms.
Yeah. I'm sure.
Supposedly to make it autonomous, so they don't have to use the deep space network anymore.
Yeah, and the deep space network doesn't work for Earth orbiters. The view periods are very short. The tracking rates are huge, very fast. And we're basically in business from the moon on. I guess as was mentioned, I've worked with international space agencies. We've been supporting the Indian Space Agency since 2008. They've had 3 missions to the moon. The last one in 2023, they actually successfully landed near the South Pole. Pardon me. Their launch vehicles are not have enough energy to launch directly to the moon or to the planet, so they launch into Earth phasing orbits. And we are able to track those with the DSN and get navigation tracking data and then help them design a maneuver that will get them on their way to the moon. Back in 2013, they launched a mission that would fly to the Mars. And we were doing the navigation. We had the DSN for the phasing orbits, and then we used that all the way to Mars. And I got to give them a lot of credit. We essentially told them where they were going to be when they got to Mars, and they designed a maneuver that got them into Mars orbit. We haven't been that successful ourselves. You're probably well aware of MCO, the Mars Climate Orbiter, where important information about the thruster firings on the spacecraft came back to the Earth, and we were told that those were metric velocity units when actually they were English. And as I mentioned, you really don't know where the target body is in time sometimes to do a maneuver to correct that. And in this case, we failed to correct it, so we incinerated the spacecraft due to that misunderstanding of why the units weren't what we thought they were. The space plane thing, well, the other thing I'm thinking about, of course, if you can use GPS in Earth orbit, then you're totally isolated from anything on the ground for tracking.
Well, this is to get rid of in case of GPS failure.
Is it? Okay. Now, there isn't one of the things that I've specialized in the 1980s, the Deep Space Network acquired a station at each of those major complexes from the Manned Space Flight Network. These stations were 26-meter stations, and the DSN was offering tracking services to any space agency, U.S. or international, private, didn't make any difference. And they wanted navigation here at JPL so that they were sure that the trajectories would meet the pointing requirements of those stations. So for 20 years, we were supporting these launches. We averaged 8 a year. We developed quite an interesting list of lessons learned from all that. And so I really got a big dose of what you need to do to launch a spacecraft and successfully acquire the signal. And that group was disbanded after about 20 years, but nobody's figured out how to leave the Earth without launching. And along the way, the thing I focus on now, and this high school teacher's son, whom I mentioned, Chris Potts, who was here, came up with a method for assessing the injection errors of the spacecraft when it's released from the rocket and converting that into the pointing dispersions at the tracking station. So you get some idea of where the spacecraft might be if there were a 3 sigma injection error, for example. And I've kind of honed that to the point that now that there are no launches, I almost don't have a job.
How about with Artemis? Are you involved with that at all?
Our section is, and it's just within the last couple of years or so, they're using the same navigation software that we are. And people in our section are involved in the navigation of the capsule, you might say. But on Artemis 1, there were maybe 20 CubeSats that were released. Often on these large launches, they provide free rides to small spacecraft, and CubeSats are all the rage these days. However, the difficulty in navigation has absolutely nothing to do with the size of the box surrounding the radio transponder. Injection errors are injection errors, and the DSN with those huge antennas is not the ideal network for doing orbit determination when you have possibly large injection errors. But we do our best.
Neil, what's your last project?
The last one, and this was at the end of July, was for NISAR, which is a joint NASA JPL Indian Space Agency, very sophisticated Earth orbiting satellite with S-band and L-band interferometry. They are continually going to be monitoring the Earth, looking for changes in land masses, land motion, all kinds of stuff. And I was on a team that assisted for the first 30 hours with the navigation for that. For the first time ever, we were going to use tracking data from the Indian tracking stations, which we had never done before.
You've been loaned out by NASA to a number of organizations, including India and JAXA and a couple of others.
The European Space Agency, it started.
ESA,
Yep.
Right?
We helped them when they flew by Halley's Comet in 1986 or so. It was the Giotto mission. And this engineer I mentioned that came up with the formulation for how you process radiometric tracking data was sought out by these navigation people. They came over here and they wanted to talk about his formulation, and they wanted to check their programs against his.
Right.
Well, he was more than happy to talk to him, but he didn't want to get involved in the nitty-gritty of comparing a couple of dozen key quantities that are vital to navigation for just one observation. And I'll never forget where I was standing when my section manager, obviously oblivious to my prowess in computer programming and my expertise with German, go to Germany and check out computer programs.
Yeah.
We have a question here in the room.
Sure.
Yes, are the signals used by the DSN impacted by solar radiation storms?
Are the signals at the DSN impacted by solar radiation storms?
Oh, you better believe it. And sometimes it's more than the signal. We've had spacecraft fried or solar panel production diminished The Japanese lost an intended Mars orbiter due to a solar flare. And in fact, the limiting error sources for navigation, a lot of them are right here on the Earth. The Earth's ionosphere, for one thing, is one of the limiting factors. We're using GPS measurements all the time to come up with calibrations to remove the effect of the ionosphere. But then you also have solar plasma. I'm a great fan of spaceweather.com, and I guess simple things awe me, but let's stop and think about it. We're looking at the surface of a star, an uncontrolled nuclear explosion just going on and on and on. And we're so blessed it's a friendly, mild-mannered star, or we would look like the pillars of creation, taken by Hubble back in 1995. And not only does it affect the Earth if a coronal mass ejection hits us, but what if it blows by Mars or blows by the trajectory of a spacecraft that's traveling from Earth to Mars or Jupiter, anywhere in the solar system, and it introduces noise in the tracking data. So you have to be very careful how you process that. And some of that space stuff, you can't calibrate out. You have to be very clever how you process that data.
Yeah.
Our mathematical models were all formed by Gauss. We haven't done anything new here.
Can you tell us about the Pioneer anomaly?
Yeah, I got involved in that a little bit, enough to see it resolved anyway. The anomaly was that after Pioneer 10 and 11, see, they both flew by Jupiter. I think they both went by Saturn. I think. I have a good memory. It's just short. And the reason we could detect this anomaly in the first place was these spacecraft were spin stabilized. Think of a rifle bullet, but it's a very, very slow. I forget what the RPM was, but it's a small number, but it doesn't make any difference. As long as it's spinning, you don't have to fire the attitude thrusters to maintain the pointing. And that's the main thing when you're flying a spacecraft somewhere. It's really nice to point the solar panels at the sun and the antenna at the Earth. And to do that, you have to fire the attitude control thrusters. And anytime you do that, of course, you're imparting a small acceleration to the spacecraft, no matter how well balanced those thrusters are. And that limits your ability as to how precisely you can determine the velocity of the spacecraft. Well, the Pioneers were spinners. And they also had thermonuclear power sources on the back side, since these were going to go into deep space, forget solar panels. And once we got past Saturn and further out into space, we also always modeled the acceleration due to solar radiation pressure. If you think of sunlight as photons that have a mass that can impart a momentum change, a key feature of our navigation software is computing the acceleration due to solar pressure on the spacecraft, which of course can be a function of the size of the spacecraft, the material in the antenna or the solar panels, and that kind of stuff. So, and that error can dominate the Pioneer situation for a long time until we get so far out that the solar pressure is no longer a domineering effect. And what we were seeing was there was an acceleration over time, and the velocity that we were computing did not match what we were observing from the spacecraft. They appeared to be not receding as fast as we thought they would. It was like there was an acceleration towards the Earth or maybe towards the sun or something like that. So there is a physicist here, Slava Jirashev, went up to Ames Research Center in Mountain View, California, which is where the project was located at Ames, the NASA center there. And literally from dumpsters, he retrieved tons and tons and tons of telemetry data. I guess some of it was on tape. I don't know what all it was. And he got funding from NASA to study this effect. You know, there were kind of thoughts: does Newton's inverse R-squared law not work in certain parts of the solar system? Or if you get to a point where you can accurately eliminate uncertainties due to solar pressure, that kind of stuff. Well, the electronics were on the back side of this huge antenna, which was maybe 3 or 4 meters in diameter. The RTG was out on an arm. It was a balanced spinner, but of course it was feeding power to those electronics. On the back side of the antenna, the front side of the antenna is basically facing the inner solar system, or very specifically, it might be facing the Earth, or there would be an occasional maneuver to make sure that the Earth still was in the beam width of that antenna. And the results of the thermal analysis was that the heat generated by the electronics on the backside of that antenna was inducing this acceleration, which appeared to be towards the sun or towards the Earth. Newtonian physics survived.
So I'm not sure if you're involved with they're planning on missions to Mars, and they're already planning some like how to get there, the different types of transfers. Normally, we use the Holman transfers to get to other planets, like to the Moon and to Mars and so on. Is there any exploration going on something like the bi-ellipsoid transfers to get there faster and then change the shape of our orbit when we get out there? So the trip to Mars is not 6 to 8 months, and we can shorten that time. Has that been investigated?
Yeah, that's certainly being considered. You know, we hope there's a surviving attempt to bring back the samples that Perseverance has cached on Mars. The European Space Agency was going to fly an orbiter to Mars and receive a canister with those samples in it. And I believe actually they were going to use low thrust to reduce the time it takes to get there. If you continuously fire a very small thruster, and we've had missions where that's been done, it's fairly common. They use xenon gas. It's ion thrusters. I kind of think of it as you cut the end off a light bulb, and the electrons spewing off a cathode impart an acceleration. And sometimes that acceleration isn't any greater than the weight of a piece of paper on your hand, but it's continuous.
Yeah. So we are looking at that for Mars missions, for human Mars missions.
No, I don't think so.
Okay.
That's a whole, there are so many unknowns there. If you just start with the radiation exposure alone.
Yeah.
I don't know how they tend to survive that, let alone the effects of weightlessness and no gravity. Musk has a lot of interesting ideas. It takes visionaries like that. You know, if it weren't for people who are willing to risk their lives, we'd still be riding horses.
All right, we will all be building our spaceships and traveling around the solar system, I guess, starting next week.
I'm sorry I can't offer you a job. I'm trying to keep my own. This budget's going to do, or lack of budget. So, Timothy, I hope you continue to recover. I'm glad that I was able to see you today.
We thank you.
Here, here.
All right. I appreciate that very much. I sent my slides to Tim Campbell, and I think I sent them to you too, Timothy. You're welcome to share those.
All right.
Thank you.
Get Melbourne's article, and then I know the next thing you'll have my job.
Point your telescope.
You don't need the Hubble telescope to impress people. You know, a 6-inch telescope, seeing the rings of Saturn. Okay, gentlemen, it's been a real privilege. Thank you. Thanks.